All right, let's move up and on. Keep working with our statistics here, and this time we're going to look a little discrete random variable. All right, check it out. Vocab, vocab, vocab. Then we're going to work it down with more vocab, so we're back. It didn't go away, is the moral of that story, right? This is stats. We have vocab, and we're rocking through it. So let's do it right now. A random variable. Let's start with that, since that is our base, right? So a random variable is a numerical measure of the outcome of a probability experiment. Of the outcome of a probability experiment. Value is determined by chance. Typically denoted by the capital letter X. Capital letter X. All right, so it's a numerical measure. That's the key here, right? So it's a numerical measure of the outcome of a probability experiment, and the value is determined by chance. That's what makes it random. All right, that's the random part of that. Okay, so a discrete random variable is finite or countable. So a finite or countable number of values. So for instance, if it's on a number line, it's the actual number 2, the actual number 3, the actual number 4. Do you see what I mean? Finite means that it doesn't go on forever. It's a confined quantity, or countable number of values, right? So it's 1, then the next one, then the next one, then the next one. So then that's what makes it countable. A continuous random variable has infinitely many values. So if I'm looking at 2, 3, 4, it's everything between them, not just the 2, the 3, and the 4. Now, I wanted both of these on the paper before we take a look at this. Have you seen these words before? Discrete and continuous? Yeah, I believe so, right? So it's the same kind of situation that we're looking at. This finite, this countable is my discrete. Continuous is infinitely many, everything that's in between that we're looking for. All right, so if we want to try to determine which one's discrete and which one's continuous, look at our examples here. Now look at this first one. It's the number of A's earned in a section of statistics with 15 students enrolled. Would that be discrete or continuous? Are they independent? Are they countable? Or is it infinite? Yes, independent and countable. I have individual students. Those are individual and countable. So this one is discrete that I'm looking at, right? Because it is countable. What about the number of cars that travel through a McDonald's drive-thru in the next hour? Again, right, this is very similar to one that we've already seen. This is the number of cars. Now, if it was the distance that they travel, that's a different scenario. But the number of cars are individual cars. Again, with the discrete. Good. Because it is countable. The individual cars. What about the speed of the car that passes the state trooper? That's continuous. Do you see what I'm saying? Because you don't just miraculously go from 15 miles an hour to 16 miles an hour, right? You increase to 16 miles an hour. That's what makes it continuous. Right? So it is continuous, and it is infinite, or it is measured. A lot of times that's how it is. As you're looking back through that. Okay, good. So the difference between discrete and continuous that we're going through there. All right. Okay. Another big definition that we want to go through now that we're in 6.1 is a probability distribution. All right, so the probability distribution, it provides possible values of the random variable x. And we know that random variable x is right here, right? The random variable, okay? See where it's coming back into play here? Okay, so this provides, the distribution provides possible values of the random variable x and their corresponding probabilities. Probabilities. There it is. So possible values that we're looking at here, these possible values of the variable x and the corresponding probabilities. All right. So what could happen? That's the possible values. What could happen here? What are my options that are available to me? Those are the possible values. And then I want to say, okay, based on these options, what is the probability that each one could happen? All right. Such as this, right? Suppose we ask a basketball player to shoot free throws, 3 free throws in particular. Let the random variable x represent the number of shots made. So you could make 0 of the 3. You could make 1, 2, or 3. That's that random variable. These are the possible options. Do you see where that's coming from? Okay, we denote probabilities using the notation P of x, that's the probability that it could happen, where x is a specific value of the random variable. We read P of x as the probability that the random variable x equals x. For example, P of 3, this possibility is equal to 0.51. Read, the probability that the random variable x equals 3 is 0.51. I'd also like to notice this is probability. Is that a percentage? No, because we have criteria associated with probability, right? This is not a percent. It is a decimal. Right? Same thing that we've already talked about in chapter 5 with probability. That's what is happening. So by that same token, there's a setup for it, and we're going to look at some examples down here. What do you think some rules are? Discrete probability distribution, but it is a probability distribution. What were the 2 rules to determine if I had a probability before? Add it up to 1, and what else? Between 0 and 1 inclusive. Don't you think those are the same? It is still a probability distribution. So we can add my probabilities up to 1. Sum of probabilities equal 1. Same thing, you guys. Still a probability distribution. Doesn't matter what kind. This one happens to be discrete. Still a probability distribution. Still same rules hold up, right? And then what was the other one? Between 0 and 1 inclusive. Good. So it's a or equal to. All probabilities are between 0 and 1 inclusive. Same criteria, right? Same criteria. That's the whole point of this. Now, look at these 3 options. You tell me. Is this a discrete probability distribution? This may be the second one, but this one is the visual. Look through here. Is there anything in there that does not fit this bill? Yes, good. This one. That's not between 0 and 1 inclusive. That is less than, right? No. Fails rule 2. What about the second one? Give it the visual. Those are all legit, right? Okay, now add them up. Put that in your handy dandy calculator. Tell me what you get. All of them. Add them all up. 1.18. Does that work? No. Fails rule 1. Good. What about number 3? Now, first of all, you guys got to know that number 3 most likely will happen here, part C, because this one failed rule 2, this one failed rule 1. We got to have one that works out right. But try it anyway. Try it anyway. Visually, this works for number 2. Add those up. What do you get? Full on 1, right? Yes. So yes, meets all the criteria. Oops, that looks terrible. Let me try it again. Yes, meets both criteria. Well, we just know that's going to happen, right? But do the visual first because that's just easier, right? So do the visual first and then add them up. Because if the visual fails, then you don't have to go any farther. Fails one, fails them both. All right. Now look at this one. We want to graph the discrete probability distribution given in table 1 from example 2. So the free throws, right? I'm going to squeeze this down so you can see this table that's up here is now down here in this graph. That's all that is all it is. All right. So there's a couple things that I want you to see. Whenever you make this graph, so here's the graph, right? We're not going to come up with the graph. We're just going to look at this graph and make sure that we're good with what's going down here. So the first thing I want to talk to you about is the vertical axis is always probability. So your vertical axis is always going to be this probability here. And your horizontal axis is going to be the values of the discrete variable. Is the values of the discrete variable. I feel like I could say that better. The horizontal axis is just those values. The number of successful free throws, that's the discrete variable part of it. All right. So when you graph a discrete probability distribution, notice how it works. It's just that line up. So it says how many is happening. And those are denoted. And then it's just this line up that goes there. Not too bad, right? Where it ends up, that's your probability. And so you can see how it plays. All right, cool.